Hello grade 12, this is physical science. My name is Gillian, and today we are looking at the big ideas of this wild topic, acid and bases, and how it fits in with equilibrium. So today what I want to do is quickly revise acids and base theory and then head into that really complicated a big idea of hydrolysis. So have a look at my screen. Let's see where we've come from, our grade 11 work. So acid-base theory started off with Arrhenius in the 1800s, and he came up with his own theory. We're going to have a look at it in a moment. His theory had limitations, and so two guys who were working on opposite sides of the earth, Bronsted and Lowry, they came up with, can you believe it, the same theory simultaneously. And so we're going to have a look at their theory as well. Part of this is knowing what ionization is, knowing what dissociation is, and working out conjugate acid-base pairs. So we will look at that too today. Now, types of reactions that we have in the acid-base section, there are 4 of them. And so neutralization is one that comes up really often, and that is an acid and a base reacting together. Then we have got 3 others, with an acid reacting with a metal oxide, an acid reacting with a metal carbonate, and an acid reacting with a metal. Now, all 4 of these reactions produce salts, not as table salt that you put on your slap chips or your food, but a chemical salt, so an ionically bonded substance. Now, pH scale. pH scale is also really important, and we deal with pH scale in quite a bit more detail in grade 12. Now, we don't have time for that today, so I'm hoping you're going to join me on my consolidation lesson, because we're going to dive into the pH scale and how to use logarithms to solve for pH. Okay, so let's have a look at our acid-base theory and Arrhenius. So Arrhenius only looked at acids and bases in the neutralization reaction. So neutralization is an acid and a base reacting together. Okay, so that was one of his limitations. It was only dealing with this neutralization reaction. He also looked at it in one solvent, and that solvent was this aqueous solution, so it was in water. So he only looked at what was happening with acids and bases in water, and so this was another limitation, that he only viewed the solvent as being water, even though there are other solvents. So what did he come up with? What he said was a base was a substance that produced a hydroxide ion, and that's called our hydroxide ions, the OH minus ion. He said that an acid was a substance that produced the H plus ion, the hydrogen ion, or another way that we know of it is this hydronium ion, that ion there. So what were his limitations? Well, as I've said, the solvent that he used was water, and so he couldn't explain acids and bases in a different solvent. And the other thing that he couldn't explain was substances that are bases that don't produce this hydroxide ion, and so there were definite limitations to his theory. So there needed to be a theory that encompassed a lot more of the other substances, and that's where the Bronsted-Lowry theory comes in. So Bronsted-Lowry is a theory that speaks about protons. So if we have a look at this hydrogen hydrogen atom that I've got on the screen, hydrogen has got 1 proton and it has 1 electron. Now, when that electron is given away, we sit with a naked hydrogen ion. It has nothing to protect it. It is just purely a single proton. And so their theory is talking about this substance, the H plus ion, and it is known as a proton, one single proton. So an acid is a substance that is going to give a proton away. A transfer of protons, that's what we're talking about here. So an acid gives a proton away. It is a donor. What about a base? A base is a substance that then takes on that proton, and so it is known as the proton acceptor. There is this transfer of protons in this reaction. It is a transfer of protons, and the whole process is called protolysis, or this reaction is called protolysis. Protolysis, the transfer of protons. What is the proton? The proton is the H plus ion. We know it as the proton. Now, we do have lists of acids and bases that are weak and that are strong. And it would be in your interest to learn these off by heart so that you know when you come across these acids and bases which ones are strong and which ones are weak. So I've put a list up here. We've got hydrogen chloride or hydrochloric acid. We've got sulfuric acid. We've got nitric acid. We've got hydrobromide. There we go, the hydrobromic acid. We've got the hydroiodic acid, and this one is an interesting one. It is hypochlorite. Hypochlorite. That po maybe helps you remember that there's oxygens involved in this one. The one at the top is hydrochloride. This one is hypochlorite. These are all strong acids. What about weak acids? Well, we've got this acetic acid or ethanoic acid. We know it as vinegar. You do put it on your chips. You can eat it. Oxalic acid is another one. There's one that I haven't put here, and this is the carbonates, the hydrogen carbonate. So that's carbonic acid. Know those. What about bases? Well, the bases that are strong all have this hydroxide ion, sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide. You can see that there's a 2 there, and that's because the calcium and the barium come from group 2, and so they have got a charge of 2+. There's one that's not there, and it might be an exception, so that is magnesium hydroxide. Now, magnesium hydroxide is actually a weak base. So learn that one. Another one which is a very interesting substance, and that is ammonia. Now, ammonia is covalently bonded, and we would expect it to react like the rest of the acids, these acids here, because they are covalently bonded, but it does not. It is a weak base. So this is an exception. This is a rebel. It is a weak base. The metal carbonates are also weak bases, and there's another one which is the metal hydrogen carbonate. So we will come across those, and you will come across those in questions. Make sure you learn them. What about the conjugate base pairs, the acid-base pairs? This is all about the accepting of the proton and the giving of the proton away. So how do we define the acid, and how do we define the base in terms of the Bronsted-Lowry theory? So if we look at this weak acid, it is carbonic acid. Why do we call it an acid? Because it is going to give a proton away. It gives just one proton to the water in this case. So this is ionization. It is an ionization reaction. And we can see on this side that the product is that it has given a proton away. It is 1 hydrogen plus ion less. And it forms that ion. So this is an acid because it is donating a proton. If we have a look at the reverse reaction, so we read it then from the other way around. We read it from the right side to the left side, we see that to form this product over here, it is going to have to take on a proton from this hydronium ion. That means it's acting as a base. Okay, it's acting as a base. It's taking on the proton. So this is what we would call the conjugate acid-base pair. They are linked. If we read from the forward reaction from the left to the right, we see that the carbonic acid is an acid, and if we read it from right to left, the reverse reaction, we see that this substance is going to act as a base. What about the water in this case? Well, the water is taking on the proton, so it is the base in the forward reaction. And what about the reverse reaction? Well, it's donating the proton, so it is going to be the acid. So this is the second conjugate acid-base pair. You will notice that the arrows are different lengths, and that is showing you that this substance, the carbonic acid, actually likes being in its molecular state. It likes being over here rather than in its ionic state, and so the equilibrium will lean to that side. It prefers to sit closer on the reverse reaction in its molecular form rather than in its ionic form. Right, ionization, grade 12s, ionization. Ionization is the reaction of a covalently bonded particle or molecule with water and a formation of ions. So when we have an acid which is reacting with water and it's a strong acid, it is going to ionize completely. It means that reaction, there's very, very little of this molecular form of acid left in solution. It really does like being in this form here, and you'll see that the arrow is only one arrow because this lies completely to the right hand side, and the acid in this case ionizes completely. It really loves being a hydronium ion rather than being in its molecular form. So when we have complete ionization, we have a strong acid. We have got a high concentration of hydronium ion and chloride ion in solution. It means that our Ka value, so that's like the equilibrium constant just for acids, so that Ka value is going to be high. It's going to be greater than 1. Why? Because there is a high concentration of hydronium ions and chloride ions in solution. So it means that there is a high conductivity, and that this solution, these ions have the potential to react well, so a high reactivity. That's what makes a strong acid. Right, we are going to take a break. When we come back, we're going to look at what is a weak acid. Hello, grade 12s. Welcome back from the break. We are now going to look at a weak acid. So what happens with the weak acid? Well, it loves being in its molecular form. It really doesn't like ionizing into its component ions, and so there really are many more molecules in solution than there are this hydronium ion and the negative ion. So this is acetic acid. We also know it as vinegar. So acetic acid is it's known as a weak acid. And the reason why it's known as a weak acid is because it likes being in its molecular form. And you can see here the arrows are showing you that that's where the equilibrium lies. There are many, many more of these full molecules in solution than there are of the hydronium ion and of the acetate ion. And so the Ka value is going to be low, and it's going to be less than 1. So it has got a low concentration of ions in this form. It means that the conductivity is going to be low, and it's not going to react that well. So what about a weak acid? It has got incomplete ionization. Incomplete ionization, whereas a strong acid is complete ionization. The same theory applies to a base. A strong base is going to dissociate completely. Dissociation, because they are generally ionically bonded. You can see here sodium hydroxide is a really strong base. What does it do? It loves being in its ionic form. There we go. It forms a high concentration of hydroxide ions. This is the hydroxide ion in solution. So there are the concentration of those hydroxide ions is high, conductivity is high, reactivity is high, and the Kb value is going to be greater than 1. Again, that Kb value is talking about the base, about how many hydroxide ions are in solution, and we call it Kb. So it's like the equilibrium constant. Now, this magnesium hydroxide, we would think is a strong base, but it is not. It does not like being in its ionic form. It likes being, there we go, as a whole substance, and so its equilibrium lies to its complete form. Magnesium 2+ and the 2OH- ions are low in concentration. What about this? The extent of dissociation is poor. It does not dissociate completely, whereas the sodium hydroxide does. So sodium hydroxide is strong. Magnesium hydroxide is a weak base because its extent of dissociation is poor. It is incomplete dissociation. It means that its Kb value is going to be less than 1. It is going to have low conductivity and low reactivity. Why? Even though it says 2 OH- ions, the concentration of those ions is very low, and so its Kb value is going to be low. What about, we've got strong and we've got weak, we've sorted that out. Now what about concentrated and dilute? Well, dilute and concentrated is talking about a volume. Strong and weak is talking about the degree of dissociation or the degree of ionization. So I have got 1 mole of both a strong acid or base and 1 mole of a weak acid or base. And you can see here that the number of ions in solution is high. So it will be a high number of ions in solution for a strong acid or base. In a 1 mole of a weak acid or base, you can see that there are very few ions in solution. The number of ions is very low because the dissociation and the ionization is incomplete. Now, what happens if I add water? What happens if I dilute it? So I increase the solvent. You can see that the volume increases, but the number of particles or ions in solution doesn't. So we still have a high number of ions in solution for a strong acid or base, whereas a weak acid or base, you can see the same amount of solvent. You can see there, so we're comparing correctly. You can see that the number of ions in solution is very low. So even if we dilute a strong acid or base, it's still going to be strong because ionization is complete. With a weak acid or base, if we dilute that, it's still going to be weak because there are very few particles or ions in solution, incomplete ionization or dissociation. We have to be careful though that we are comparing correctly. So you can see that my comparison is fair, 1 mole versus 1 mole, and you can see that the amount of solvent is the same over here. I hope that helps you, grade 12s, with the concept of strength versus concentration and dilution. Right, grade 12s, it's heating up here. There are 2 more topics that I would love to cover in this time. The first one is titrations. So we're going to have a quick look at what those are. And then the other one is hydrolysis. So let's skip on to titrations. So titrations revolves about a single reaction, and that reaction is neutralization. It is a salt-forming reaction with an acid and a base. So an acid and a base, when they react together, they form a salt and water. Now, titrations, that's a big word. We need to know what it is. It is the name for a technique that we use in the laboratory, and it involves specific equipment. So you can see in my picture here, we have a pipette, we have a burette, which is a weird instrument. It's like a long straw with a tap on it, and we can regulate how we run the liquid in the top through down to the bottom. We have a conical flask, and we put one substance in the burette, let's say the base, we can put into the burette, and we put the acid into the conical flask. It can be the other way around, but these substances generally are see-through. We can't see them. So we will never know when this reaction reaches neutrality, when the acid will neutralize the base or vice versa. So we need to add in there an indicator. And the indicator is really important when we are doing calculations. There are 2 words that you need to know. The one is endpoint. Now the endpoint is where the indicator actually changes color. Now there are 3 colors for the indicator, 1 in the base, 1 in the acid, and then there's a slight change in the indicator color as this endpoint is reached, and that you need to be quite precise about, and you need to look at it, good observations with your eye to check where that endpoint actually is. The equivalence point is the other word that you need to know, and that is where that's talking about the chemical reaction. And equivalence point is where the acid completely reacts with the base, or vice versa, where the base completely reacts with the acid. So now we delve into this chemistry in more detail when we're speaking about hydrolysis. So the titration has happened, the neutralization reaction has happened, and now we get the product, which is salt and water. And we're going to look at what happens with that salt. So that salt, the results, the product of this neutralization reaction, reacts with the water. And we can have hydrolysis happening. This is the official definition for hydrolysis. So a salt can hydrolyze, there we go, with water, which may cause a change in the pH of the solution. When we titrate a strong acid and a strong base together, we know that the pH at the end of this reaction is 7, or around about 7. And that explanation is given very nicely in the videos that have been preset for you to watch. So I'm not going to go into that. But what I do want to do is have a look at where we have acid and base that are not of the same strength. When we've got a strong acid and a weak base, and a weak acid and a strong base, what happens? So here's an example of a strong acid and a weak base. We have the salt forming, which is ammonium chloride. Now, when we want to see what the acid is and what the base is, we look at the ions of this particular salt. So we've got the NH4 plus ion, which is the ammonium ion, and we have the chloride minus ion forming. So the anion is the chloride minus ion. That comes from the acid. So what acid will give us a chloride ion? It would be HCl, and we know that that is a strong acid. What about the base? Well, ammonium must come from ammonia, and we know that ammonia is a weak base. Now, what happens when we take the salt and we put it into the water that has formed? There is going to be some dissociation into these ions, the ammonium plus ion and the chloride minus ion. Now, we know that the ammonium comes from a very weak base, which is ammonia. That's weak. It's the weak base. So its conjugate pair is going to be a strong acid. So that's the ammonium ion is going to be a strong acid. Chloride minus ion, that comes from a strong acid, and therefore it is a weak base. So it is not going to do anything. It likes being in that form. Weak base means taking on a proton. It's not going to do that. It's weak. It likes being in its ionic form. But what about this ammonium ion? So the ammonium ion is a strong acid, which means that it is going to give away its H plus ion, its proton. It's going to give it away. And so this solution, resulting solution that we're going to have is going to be slightly higher in the proton concentration. So its H plus concentration is going to be slightly higher, and that is going to affect the pH, and so it gives us a pH that is slightly acidic. So when we have a strong acid and a weak base that are neutralizing each other, the resulting salt is going to be slightly acidic. It's an acidic salt that is formed, and that solution, resulting solution, is going to be slightly acidic. The pH is then going to be just below 7, just below 7. So the pH in this case, the pH is going to be a little less than 7. What happens when we have a weak acid reacting with a strong base? Now, here's a salt, which is the acetate, the sodium acetate salt, and again, we're going to have a look at the ions. So this is the negative ion. This is the really weird way of writing it. The organic chemists like writing things the opposite way, and so it makes us a little bit confused. But we can handle that. So the acetate ion is the negative ion, and so that is going to be, that's going to come from the acid. So this will be acetic acid vinegar, or that CH3COOH. The cation is going to come from the base, that's sodium, so it's going to be sodium hydroxide. Okay, so we know that that is the strong base. This we know, the vinegar we know is a weak acid. Now what happens when we have a look at the products? So this salt is going to dissociate or ionize into its component ions. We know that this comes from, the acetate comes from, is a weak acid. Okay, it comes from a weak acid. The acetic acid is weak. Therefore, its conjugate base is going to be strong. So here's the conjugate base, the acetate ion, and that's going to be strong. What does it mean? It means that it's going to grab onto those protons. The H plus ion is going to grab onto it. Why will sodium not participate? Why will it be quite happy? Well, it comes from a very strong base, so it is a weak acid. it's not going to be wanting to do anything. So it stays in its ionic form, but this acetate ion is a strong base. It wants to grab onto those protons. It takes those out of solution, and so we end up with quite a high concentration, well, not quite a higher concentration of the hydroxide ion. That means that this salt, which is formed, is a slightly basic salt, and it forms a slightly basic solution. So the pH of this solution is going to be a little bit higher than 7, just a little bit higher than 7. Right, grade 12s, I hope that has given you some clarity around hydrolysis. See you in the next lesson. We're consolidating and we're going to have a look at the pH scale, so please join me then.